Okay, so we're going to take a look at some of the online homework. Let's see. So I've selected the first one that we're going to take a look at for this set. It says a certain spring stretches 5.4 centimeters when it supports a mass of 0.88 kilograms. If the elastic limit is not reached, that's a little bit of housekeeping. It basically means don't worry about the spring bending and breaking and doing extra stuff. It'll act like a normal, ideal spring like we've been working with in class. If the elastic limit is not reached, how far will it stretch when it supports a mass of 10 kilograms, a much larger mass? So we've got a spring. Helps if I unfreeze this. There we go. We've got a spring here. And it has some natural length that we may or may not know. Natural length of question mark. Doesn't actually tell us. It does say that if we hang a mass equal to 0.88 kilograms, that it stretches out, the spring stretches out by a value of 5.4 centimeters. And then they're asking us if instead, if we were to hang a mass of 10 kilograms, how far would it stretch out? All right, now I've drawn that much larger because 10 kilograms were getting very heavy at that point. It's about 22 pounds. That's not light to put on a spring, especially when what we first put on was about 2 pounds. So here's what we're going to do. This is kind of a complex problem. We're going to need to do 2 steps in this. First, we're going to want to find something that is in common between these two. Well, it's the same spring, so what we really need is the spring constant, K. So we're going to take our data here, or our information, I should say, here at the beginning and find our spring constant. We're going to use Hooke's law. We know that the force of a spring is going to be equal to negative K delta X. All right, well, in this case, let's see. We need to find the force we've applied to the spring, and we need to find the displacement. Well, the displacement should be pretty easy. Delta X is going to be technically delta Y. We hooked the mass on, and it went down by 5.4 centimeters. We're going to need to convert that over to meters, 0.54 meters. It's a factor of 100. I'm going to help you out with that, but as a reminder, in class, you are expected to be able to work with kilo, milli, and centa at any given point, so you'll need to be able to convert these on your own. We know that we've got that displacement. In fact, I'm going to put a negative because our displacement is downward in the y direction. Now, we're also going to need to know about the forces involved, and for that, we're going to do a Freebody diagram. So, I have a mass hanging on there that is pulled down with the force of gravity and held up by the force of the spring. I do Newton's second law and apply that on there just like we did in class, and we find that the force of the spring minus the force of gravity is equal to our mass times our acceleration in the y, and when the mass is just hanging there, our acceleration in the y is going to be 0. That tells us that our spring force must be equal and opposite to the force of gravity, not because of Newton's third law. This is not an equal and opposite reacting pair. They happen to be equal and opposite because of Newton's second law, and this object is not accelerating. The mass is just hanging there. We also know that the force of gravity is equal to mg, which will be 0.88 times 9.81. With some units, we'd have kilograms times meter per second squared, and I would find the following, 0.88 times 9.81, and we get that our force of gravity, and therefore our spring force, must be equal to 8.63 newtons. About 8.633, but 3 significant figures should be fine. All right, now that I've got my force, it is up. My displacement is down. We can go back over to our Hooke's law equation, and we know that the force, spring force, is equal to negative K delta X, both of these being vectors. We have a positive 8.63 newtons, because the force is up, equals negative K times negative 0.054 meters. Negative because our displacement is downward. Our object is moving down. The negatives cancel out, as they should. We should end up with a positive spring constant. If you end up with a negative, there's a good bet that you misplaced a negative somewhere, so take a close look. We can solve for k by dividing both sides by 0.054 meters. We find that the spring constant, at least for my numbers, comes up to 8.63 divided by 0.054. I get the following. 159.8, so I could call it 160. 160 newtons divided by meter, Newton per meter, which is what we expect for a spring constant. All right, great. Now we've got the spring constant for the spring. And when we take the mass off and put a new mass on, we know that we'll have the same spring constant. So we should end up with a spring constant of about 159.8 or 160 should be fine, newtons per meter. All right, let's go through and let's finish this up. This was not our answer. We were not asked for the spring constant. We were asked for what the extension of the spring is going to be when we put a 10 kilogram mass on it. Well, we'll once again need to draw a free body diagram and the forces, but we're going to find that once again, the spring force is going to have to be equal and opposite to the force of gravity. Not because of Newton's third law, but because of Newton's second law. We're going to hook the 10 kilogram mass and let it come down until it comes to a stop and just let it sit there. So we call that an equilibrium position. That's where our forces are balanced. I'm going to save a little bit of time, and we know that the spring force must be equal to 10 kilograms times 9.81 meters per second squared. That'll be the force of gravity on this new object. We know that the spring force under these new circumstances will be 98.1 newtons. We also know that for, let's see, FSP is going to be equal to negative K delta X. We find the following. We said that our force is going to be 98.1 newtons equals negative 159.8 newtons per meter, or 160 if you prefer, times delta X. Now, we want to solve for delta X, so I'm going to divide both sides by negative 159.8. Let's go through and check this. 98.1 divided by 159.8, or 160 if you prefer. And there's a negative in there. We end up with negative 0.614 meters is going to be equal to delta X. Now, we've got the negative because that tells us direction. That tells us that we displace downward. Our spring stretches out. When we put our answer in, they're probably asking us specifically how much does it stretch. In fact, it says how far will it stretch when supported by the mass. So we're going to take just the magnitude, the absolute value. So what we're looking for is delta X equals 0.614 meters. And they, I believe, instruct us to answer in centimeters. If not, they gave us information in centimeters, so I'm pretty certain they want the answer in centimeters. So delta X, we're going to need to convert this over to centimeters. We get about 61.4 centimeters. Let me check my answers. We get 61.36 centimeters is what they have listed. So the correct answer is 61.4 centimeters. So there we go. That one's a bit of a compound problem.